Okay, so now let's look at the third subtopic in the atoms and nuclei topic, radioactivity. And I think this is one of the more interesting subtopics in the Year 12 physics course. Radioactivity has, I think people probably don't realise how important it is to both science and to people's everyday lives, and the extensive amount of applications that use it. And I'm not going to talk about all of those, but I'm just going to touch on a few. Radioactive isotopes are extensively used in both diagnostics, so that's working out what's wrong with people, and therapeutic medicine, so that's treating various conditions, particularly cancers. Not such a common thing, but one of the things I think that is really neat is it's actually the decay of radioisotopes, which is one of the reasons the core of the Earth is so hot, and why we sit on this, the crust of the Earth sits on this molten core of magma, and then obviously deeper down we get to a solid iron core in the centre of the Earth. It's used to date geological formations and rocks, and also historical artefacts through things like carbon dating or uranium dating in the case of rocks. And another one that probably a lot of people don't realise, but a lot of food is actually treated with radiation to kill bacteria, and it's also used to sterilise medical equipment. So these are all applications of the radioactivity topic. The main one we're going to focus on here is a diagnostic medicine one at the end. PET scanning ties in with what we looked at the cyclotron. We'll get to that at the end of the topic though. So within our universe, we have a lot of stable atoms or stable nuclei, but we also have some unstable nuclei. So the stable nuclei will essentially pretty much last forever. However, the unstable nuclei at some point will decay, and what we're really going to learn about now is why they decay and how they decay. So and we're going to use what we learned in the last subtopic about the structure of the nucleus to explain a lot of this. So if we look at this graph, and we're going to use this graph a little bit in the next two slides, so stable nuclei of low mass have approximately equal numbers of neutrons and protons. So in this region here with the low atomic number, we can see we have basically a straight line relationship. And if we look here where we have an atomic number of 25, we have a mass number of 50, i.e. 25 protons plus 25 neutrons. So in this sort of first 20 elements region, we tend to have a 1-to-1 ratio of protons to neutrons. However, the stable isotopes that we know of start to sort of bend up past this 1-to-1 ratio. So this line here indicates the 1-to-1 ratio, and they start to bend up beyond this as we get to heavier elements. So basically the stable nuclei in this range have more neutrons than protons. And then we get to this limit, which is at an atomic number of 83, past which there is no stable isotope. We can't make or find a stable isotope with an atomic number, so greater than 83. So a nucleus with more than 83 protons within it. So what causes this? Well, as we talked about in the last subtopic, electrostatic repulsion between the protons with the nucleus should push the nucleus apart. The repulsive electrostatic force within a nucleus is countered, though, by an extremely strong short-range force, the nuclear force, and that is an attractive force between nucleons, so both protons and neutrons. So the way I like to think of it is that neutrons, which don't have the charge, so we don't have the electrostatic repulsion, act like a nuclear glue helping to hold together the protons. As the number of protons increases and as the atomic number increases, the number of protons obviously increases, the repulsive electrostatic force increases, and more neutrons are required to provide the nuclear glue to stabilise the atom. It's a bit of a simplified explanation of why the number of neutrons increases from this 1-to-1 ratio, but I actually think it's probably sufficient for everything we're going to look at in this course. So let's get into now and look at why other nuclei than the ones, if you like, shown on this graph are not stable and how they decay. So, unstable nuclei undergo a process of decay by the emission of radiation. So basically, the reason we get radiation is because unstable nuclei decay, and in doing so, they release these high energy particles that we know as radiation. So there's 4 types of decay. We can get alpha decay, in which a helium nucleus, or also known as an alpha particle, are emitted. So that helium nucleus consists of 2 protons, 2 neutrons. So we often indicate that like that. We can also get the release of we can also get beta minus decay, in which an electron is emitted. And importantly, this electron is emitted from the nucleus. So it's not like one of the electrons that surrounds the nucleus is emitted, as in ionization that we talked about when we talked about the structure of the atom. This is an electron that's emitted from the nucleus. We can also get beta plus decay, in which positrons are emitted. So a positron is a positively charged electron. So same size, same mass as an electron, but it has a positive charge. The final type of decay, and we're not really going to focus much on that at all in this course, is spontaneous fission, in which a nucleus splits into 2. So basically, a large atom can split into 2 smaller atoms. That one is quite random in its sort of nature and quite hard to predict, so we're not going to look at that in any detail. So, the types of decay correspond predominantly to 2 to 3 regions on an N versus Z graph, or in this case I've got an A versus Z graph. So this is the same graph that we had before, where we have our mass number, which obviously represents the number of neutrons plus protons, and our atomic number, which represents the neutrons. We have our 1-to-1 ratio. Okay, so if we have an atom that is too large, which is basically anything beyond 83, this atom will try and reduce its size by either undergoing alpha decay, which is the one we're going to focus mostly on, or it could also undergo spontaneous fission. But we're not going to worry too much about that. So essentially, if you try and put more than 83 protons into a nucleus, the protons at either side of that are so far apart that the short-range nuclear force can't hold them together. So those protons will push apart, and that atom, while it may last for a certain amount of time, and in some cases quite a long time, will not be stable indefinitely, forever, for eternity. So if the atom is too big, we get alpha decay. Now, the next region we will look at is if we have this region here, just above the line of stable isotopes. So we call this, if you like, too many neutrons. So if an atom has too many neutrons, a neutron will be converted to a proton, and in the process of this happening, to conserve charge, we talked about conservation laws in the last subtopic, we will get the release of a beta minus particle, or an electron, so a negatively charged particle. Because a neutron has no charge, if that turns into a proton with a positive charge, a negative charge must be created to balance out that positive charge of the proton. If we have a case where we have not enough neutrons, you might think of it, or too many protons, so this area along the bottom of the graph here, then a proton will be converted to a neutron, and we'll get the release of a positron, so a positively charged particle. So if a proton with a positive charge turns into a neutron with no charge, we need to get a positively charged particle released to conserve charge. So they are the 3 regions of our graph and the corresponding types of decay that happens in each of those regions.